In this video, I'm going to talk about concavity and the second derivative test. Yeah, there are two of them. While the first derivative test tests for functions that are increasing or decreasing, the second derivative test tests for functions that are concave up or concave down. But we first have to know what concavity even means. So let's go ahead and define it. Concavity is a behavior. Concavity is determined by the behavior of the first derivative of the function. So there's two kinds of concavity. So concave up is when f prime of x is, f double prime of x is greater than 0. And concave down is when f double prime of x is less than 0. And just so you know what concave up looks like, so if you have the graph of f of x, I'm going to draw two graphs. So a function that goes like this is concave up, and a function that goes like this is concave down. It's kind of like if you think of the function as a cup, and whichever way is open is the way that's concave. So for example here, if we treat this like a cup, the cup's facing up, so it's concave up. Here, the cup faces down, so it's concave down. But with these definitions, we can do a little more than this. So we notice that concave up is when the second derivative of f is greater than 0. But the second derivative of f is the first derivative of the first derivative. So this can also mean when f prime is increasing, right? Because this is the derivative of the derivative. So when the first derivative is increasing, the second derivative will be greater than 0. And likewise, when the second derivative is less than 0, that means the first derivative is decreasing. And another thing is, so for first derivatives, where the first derivative changed sign, those were critical values. So critical values are where the first derivative changes sign, or the function f of x goes from increasing to decreasing, or vice versa. Like so. And for the second derivative for concavity, we call them points of inflection. And points of inflection are where f double prime changes in sign, or when f of x goes from concave up to concave down, or vice versa. Okay, let's see all of these on a graph. All right, so this is like the same graph I always use, but all right, I have a graph. Now I want to find me the critical values, right? So remember, critical values are when f prime changes sign, or when f of x, this is the graph of f of x, or when f of x goes from increasing to decreasing. So right here, f of x goes from increasing to decreasing. So this is a critical value. And here, f of x goes from decreasing to increasing. So this is also a critical value. But notice here, or around here somewhere, the function changes from concave down to concave up. And this is a point of inflection. Right, so again, when the function goes from increasing to decreasing or decreasing to increasing, those are critical values. When the function goes from concave up to concave down or concave down to concave up, those are points of inflection. And the same way we found the behavior of increasing or decreasing functions with the first derivative test, we find the concavity behavior of functions using the second derivative test. Now that you know what a point of inflection looks like on a graph, let's go find them analytically. So if you'll remember, we found critical values by setting the first derivative equal to 0, because that's where the function changed from increasing to decreasing or decreasing to increasing, and we need to find those, boundary values. Well, for points of inflection, since we're trying to find concavity, we're going to set the second derivative equal to 0 and then solve for x, because we're trying to find where the first derivative goes from increasing to decreasing or decreasing to increasing. It's the same as the first derivative test, just one rung down the ladder. All right, and this is a nice way to go to second derivative test. Like the first derivative test, I'll walk you how to do the second derivative test. So here, instead of finding the critical values, we're going to find the points of inflection. And again, I'll just use some arbitrary values, x equals a and x equals b, with b bigger than a. All right, the second step is to make our intervals. You'll see this is very similar to the first derivative test. All right, so we're going to have, and again, this has to span the whole number line. So we're going to go from negative infinity to a, from a to b, and from b to infinity. All right, step 3 is pick a value, or pick points, whichever you prefer. And I'm going to use the same letters as last time. So say C is in this interval, D is in this interval, and G is in this interval. And for the fourth step, we find the sign not of f prime of x, but the sign of f double prime of x. Right? Because we're trying to find where the first derivative is increasing or decreasing, and we do that by determining what the second derivative is doing. So we need to find the sign of f double prime of c, sign of f double prime of d, and sign of f double prime of g. And finally, we make our conclusions. Okay, I'm just going to go and say, here there's a plus, minus, plus, right? Because these are all arbitrary numbers. Okay, so from this information, we can see that here immediately, the plus means that in this interval, the function is concave up. And if you see negative, that means it's down. And here it's positive, so we say up. But unlike the first derivative test, where we could go in between and make more conclusions, the second derivative test stops here. Let's do an example problem. We're asked to conduct the second derivative test on this function, So we have to find the intervals where it's concave up and down. So to start, we first have to find our points of inflection. So I'm going to go ahead and find the second derivative. Here's the first derivative. And here's the second derivative. Now we need to consider, oh, by the way, when you're finding points of inflection, you also have to consider when the second derivative is undefined too. So let's consider it here. Can this ever be undefined? No, because this is a line, like something like that, and it's a polynomial function, so it can never be undefined. So we're good on that. So now, just like how I found critical values, we're going to set this equal to 0 and solve for x. I'm going to subtract 4 from both sides and divide by 6. All right, so we have a point of inflection at x equals negative 2/3. So with this information, I'm going to make my intervals go from negative infinity to negative 2/3 and negative 2/3 to infinity. Right? Since there's only one point of inflection, there's only two intervals we have to consider. All right, now we have to pick our point or value. And just pick an easy value for this. Don't make your life any harder than it already is. So I'm going to do -1. Here I'll do +1. All right, now for the sign. What is the sign of f double prime of -1? Well, all right, f double prime is 6x plus 4. And f double prime of -1 is -6 plus 4, which is -2. So this is negative. And then sine of f double prime of +1 is, so we have 6 plus 4 is 10. So we have a plus. Okay. And now, using these signs, we can conclude that from negative infinity to negative 2/3, this function is concave down. And from negative 2/3 to infinity, this function is concave up. And I'd imagine if you graphed it, it would look a little something like this, where this is x equals negative 2/3, like that.